Question is a very, very good question. Sig figs with our homework site. I'm all kinds of sig figs are important. You have to pay attention to them because you only know so much. You don't know all of this. You only know this amount, and you need to reflect that. But the homework site, and I have used, I think, 4 computer web homework sites, and not one of them deals with significant figures correctly. In fact, most of them just don't try. And that's the approach that this site takes. It just doesn't try. So what they do is they check all of their answers to 4 significant digits, no matter how many digits you actually have. And then if that doesn't give you the correct answer, then they try to find, okay, so, what if it was only this amount? So basically, for the homework site, pretend you don't know about significant figures. Okay? And I'm sorry about that. That's not the way I would make the world work. Yes?
Should we input 4 sig figs all the time?
Yeah. Just put in 4 sig figs all the time, and it should be good.
No rounding of any kind?
Well, you do... Actually, I was going to say, you do know how to round. Most people don't. When I was a youngster, my teachers taught me craziness like 2.5. If I round that, was that round 2? Yeah, my teachers didn't know how to round, and they said that went to 3. But that's not right. Nope. That's not right because it puts in a systematic bias to your rounding. So the more you round, the more your numbers get larger if you use that. So the scientific rounding, the way that you should round, which like I said, most people don't learn this, is you round to the even. So 2.5 would round down to 2. 1.5 would round up to 2. And so you round to the evens if it's exactly 5. Just since you brought up rounding. Because, like I said, most people just didn't learn to round. They learned the simple first, third, whatever grade rule of round up on a 5. But yeah, it adds a systematic error. And we don't want systematic errors. Okay.
Theoretically, wouldn't that just add another systematic error towards even numbers?
No. Even numbers is not going to shift your answer up or down. And on average, if you do 10 rounds of exactly 0.5s, if you're doing the rounds to the even, on average, you'll done as many ups as you did downs. Hmm? 0.5. That 0 is the... I know 0, some people might say it doesn't count as an even number, but yeah, it's following that sequence it is. Yeah.
Do you want that to be the rule when you have exactly 0.5? Or
yes, it's only when it's exactly 0.5. This is 0.50001. Yeah. Yeah, so if it's like 0.53, you don't say, oh, well, I'm going to... 0.53, you always are going to round up. Okay, kinematic equations. Last class period was our Flip Friday, and I obviously grossly miscalculated the time it was going to take. And I'll tell you how I'm going to grade those. I haven't graded them yet because I spent all day after football yesterday. I had to go watch the boys play some football, even though I'm, injured. But I spent all day after that until the Raider game grading labs, and I'm pretty close to having those graded. So I don't have the Flip Friday stuff graded yet. That will be done after the labs are graded. What I'm going to do is go through and find the people who got the least done and grade out of the number of answers that they got completed. Now, if somebody got more than that, I will bring it down to that so we won't have people that got 120% because otherwise you didn't really grade off of that. You just said, okay, those people get 100% and everybody else gets extra credit, and you still spread people apart based on speed. But what that will do is allow, like there were a few people, I know there's one person, I'll say your name, Chad forgot to do the pre-part, but he did get all the way through. And it gives him a chance to get a pretty good score because he went faster in class and he can use some of that to cover for mistakes earlier. So basically, let's say it comes out to a total of 20 possible for the people who got the farthest. Then I'll grade everybody's. And if you scored higher than 20, it'll come down to 20. If you scored lower than 20, well, it'll be what you scored. Sound fair? I mean, I want to be fair, obviously. I don't want to be punitive and that kind of thing. Okay, so because we didn't get done with that, I clearly didn't have time to go over it like I had planned in class, and I didn't have time to actually explain the kinematic equations. So today in class, I'm going to be explaining how to solve problems with those kinematic equations that we were learning about. So over here, I have listed the 5 equations the textbook listed as kinematic equations. And I will talk briefly about where these come from. So let us start with the simplest one on this list, the average. If I have a nickel in one hand and a dime in the other, how do I find the average of the 2 coins? Add them together and divide by 2. So that's all that is. That's not really a kinematic equation. The book lists it as a kinematic equation, well, because it does relate to kinematic variables, the speed. You'll notice I put V with the subscript of average for speed. All of these I put as scalars, that is just values with no direction. So that one, that's pretty simple. That's just knowing what it means to take the average between 2 values. I should mention there is another thing up here that is implied that I didn't write. It is specified in the textbook. These equations are only true if you have constant acceleration. If you don't have constant acceleration, then you're going to have a different average equation even. This was taking the average between the beginning and the ending speeds. The V0 was the starting speed, the V was the ending speed. Taking the average between the beginning and ending, assuming that the speed was changing at a constant rate. What do we call the rate at which speed is changing? The acceleration. So that was assuming constant acceleration. If the acceleration is not constant, if you start at this speed and you quickly get up to maximum speed and then go for a long time at maximum speed, how is your average speed going to compare to the starting and ending speeds? Halfway in between or closer to one than the other? Closer to the ending one because you were at that speed for a long time. Right, so this equation only applies if it's constant acceleration. Remember that V0 is the starting speed and V is the ending speed. Now, these 2 equations, let me change color. These 2 equations here are pretty similar in their origins. They come from the definitions of speed and acceleration. Now, I didn't carefully go through those definitions yet, so let me write them down. Actually, I did write this down. V average is equal to x minus x0 over t. Now, that's not the way I wrote it in class last Wednesday. Last Wednesday, I put delta x over delta t. Why are those 2 equivalent equations? It's important just that we understand the assumptions that go into making those equivalent. So why are those equivalent? Okay, delta means changing, so delta always means final minus initial. X, we're using to say x final. X with the subscript of 0 means x initial. So this x minus x0 is delta x. Now on the bottom we just have t, and here it had delta t. How are those equivalent?
Just assume that t initial is 0.
Right, that has the further implied t sub 0, the starting time is 0. And so with those things understood about the nomenclature and our arbitrarily setting t sub 0 equals 0, those are equivalent equations. Now if I take it in this form and just solve it for x, I'm going to have to multiply both sides by t. So I'll have V average multiplied by t is equal to x minus x0. And finally, move the x0 across, and I'll have x is equal to x0 plus v average t. So that is this equation right there. So that's basically just the definition of what v is. The lower one here, that's relating speed and acceleration. Now, I don't think that I ever actually wrote the equation for acceleration. So the equation for acceleration there's the way we would usually write it. Change in speed or change in velocity, if you're talking about, actually, it really does need to be change in velocity, is the truth, divided by change in time. If you're one-dimensional motion, then you can write this, okay, I'm putting vector signs, so that's absolutely correct. That's the true definition of acceleration with the vector signs. Vector sign means it has magnitude and direction. So in one-dimensional motion, I can put A average is equal to V minus V initial over T, using the same definition that V is the speed at the end, V0 is the initial speed, and time 0 was 0, so that delta T was just the time. So for one-dimensional motion, this here is correct. And then using exactly the same math steps, this solves to V is equal to V initial plus A average T. Now this equation has one thing different than this equation. What's the one thing different? One says A and one says A average. A is equal to A average if you have constant acceleration. So they are the same because these are only for constant acceleration. If you have constant acceleration, A is A average. And so you go from there. Now, before I go to the other equations, a couple important things. With this V average, the average speed or the average velocity. What's the difference in average speed or average velocity? Well, the average velocity, as I talked about, is the change in displacement divided by time. And so it's going to have a direction to it. And if I do something like a complete lap and come back to my starting point, so my displacement was 0, then I would have 0 velocity, because my change in displacement per time was 0, even though my change in position, the distance I traveled, was definitely not 0. And so my average speed wouldn't be 0, my average velocity would. If you decrease the delta t, then the average velocity and average speed move closer and closer to instantaneous values. The speed you have at a moment or the velocity you have at a moment. And when you get to an instantaneous velocity, then the instantaneous velocity is the speed with its direction. So we have to have these ideas in our head just so the words don't confuse us and we keep in mind the difference in an instantaneous versus an average. Now with the acceleration, this being the true definition of acceleration, anything that is a change in velocity is an acceleration. So, Jared, give me an example of a change in velocity.
A
Car.
slowing down.
Slowing down. Okay, car slowing down is a change in velocity. Why is it a change in velocity? Because the velocity is the speed and the direction. If it's slowing down, its speed is decreasing, that's a change. Now, if you have a car that's slowing down, our textbook has the word deceleration in it. I don't like the word deceleration because it can get things confusing. Deceleration, according to our textbook, is an acceleration in the opposite direction as the velocity. Hence, by definition, when the car is slowing down, it's decelerating. I like to just use the term acceleration and pay attention to the direction, and I don't get confused like can happen when I use the word deceleration. The textbook points out very carefully that if the car is traveling forward and slows down, it's decelerating. If it's traveling backward and slowing down, that's also decelerating, but the accelerations were in opposite directions. If I'm going forward and slowing down, what direction is my velocity changing? It's changing to the rear. If I'm going backward and I slow down, what direction is my velocity changing? To the front. So the velocity and acceleration can be opposite directions because acceleration is about the change in the velocity, not the actual velocity itself. And either one of those were examples of deceleration. Now if I'm starting from rest and I start speeding up, what direction is my change in velocity? Forward. Hence, what direction is my acceleration? Forward. Okay, so just some simple examples there of acceleration, what it means and how to deal with it. You'll have lots of experience, but that was just one example. What's another example of acceleration, Chad?
Of acceleration?
Of acceleration. Besides speeding up or slowing down.
Circular motion.
Okay, changing direction. If I'm driving my car and I'm going at constant speed, but I make a turn, my velocity went from this direction to that direction. Those are not the same. Hence, there was a change in velocity, and the acceleration is the rate at which the velocity changed. And we'll learn more about the centripetal acceleration, the acceleration necessary to make you go in a circle, what Chad was referring to there. But it's important that we understand changing direction is also an acceleration. It's also causing a change in velocity. So when you're driving your automobile, and you sing, "Riding along in my automobile," because you do that, right? When you're driving your automobile, what instruments or pedals or whatever do you have that will accelerate your car? Michaela? The gas pedal. We often call the gas pedal the accelerator. You press on the gas pedal. About 4 years ago, I bought a new car. Now when I press the gas pedal, it actually speeds up. That's what's supposed to happen. I used to have an older car, and you press the gas pedal, and initially you'd slow down a little. Then you'd speed up. But either way, it was really accelerating you, right? Because even if I press the gas pedal and I slow down, that's an acceleration. Okay, so the gas pedal changes your acceleration, or causes an acceleration because it changes your velocity. Okay, Diksha. What's another instrument you have that will accelerate your car? The brake. Because you press on that brake, and it's going to slow you down. Whether you're going forward or backwards, it's going to slow you down, and so that's going to cause a deceleration. Charnay, there's one more. The steering wheel. Why is the steering wheel? The others, I explained why they were correct. You, I'm asking why are you correct?
Well, you can turn it and it'll change
It'll change your direction. So you have three things in the car that realistically we could call accelerators. But of course, we're used to just calling the gas pedal the accelerator because it causes a forward acceleration. Okay, I've explained how we got these two equations from this list plus the definition of acceleration. The final two take more work. Now, in the calculus class last Tuesday, I showed that by doing straight integration, this equation, boom, is quick and easy. Without calculus, you can still wave your hands to show that it's correct. You can say, okay, so the position is equal to the starting position plus the average velocity multiplied by time. But average velocity is the starting velocity plus the ending velocity divided by 2. And so if I put this equation into here, then I will get, and I actually have to do that because I don't know what I'll get. I mean, I know where I'm ending up. Okay, I think I put that all in correctly, right? Right? But then if we look at the equation for speed as a function of time, this equation, to put that one in as well, forgot to put the 1/2 there. Now, did I do that right? No. No, there's only 1/2. I was right. So here I substitute for V, I put V0 plus AT. And now, bring my terms together. I have a V0 over 2t, and here's a V0 over 2 times t as well. So I have 2 of those, making it plus V0t. And then I'm left with this term here. And so that's how you can get that equation without calculus. It's simpler and makes more sense with calculus, but without, you can see, okay, it works as long as we are in the restriction of acceleration being constant. And truly, this equation only works if acceleration is constant. Now, this last equation, I'm going to erase all of my marks now. This last equation, this one here, you get by eliminating time. So I have an equation here. Can you see what I'm circling? Yeah, you can. Okay. So I have an equation here that has time in it, time 2 places, and then I have this that has time or this that has time. I'm not going to go through the work because I don't want to, but by eliminating time, you can get that equation to modify to this. So we have our kinematic equations, and of these equations, those 3 are the ones that I generally consider the kinematic equations. Those are the ones I use to solve the problems, such as you have in the homework that's due tonight, 11:55. One of those 3. Now, whenever you're doing a problem, we have the equations, we all have our math skills, but we need to have a strategy for solving the problem. And the first and most effective piece of strategy to note with these is the variables involved. So if we look at this first one, the variables it has are x, x initial, v initial, acceleration, and time. It has a total of 5 variables there. Those are pretty much all the kinematic variables. There is one variable in the second one that was not in the first. It has v, v0, a, and t. So this one has the final speed. This one didn't have the final speed. Final one here, x, x0. When I look at these, the keys I look for are what variables are not present. So if you look at the second one, it has no position data. So if you're looking for a problem and it deals with time, acceleration, speed, but not position, that's probably the one you want to use because it's the one that has the variables you're looking for. If I look at the bottom one, what variable is it missing? So if you're looking for a problem and it doesn't give you time and it doesn't ask you for time, that's your most likely equation to work with. This one here has pretty much all of our kinematic variables. You could say, well, it doesn't have speed at the ending time. That's the only thing it doesn't have. This is the one you use, I estimate, around 90% of the time. Around 90% of the time, you have all the variables in play. And that's the one you use. But look at the variables you have. If you don't have position and you don't care about position, well, then you just use the v equals v0 plus at. If you don't have time and you don't care about time, then you use this one. One final statement about these equations before I move on to working some problems. Well, actually, I'll explain the figure on the left first and then work some problems. Is vectors versus non-vectors. All of the equations above the soon-to-be black line, non-horizontal black line, I might add, all of the equations above that are actually vector equations. I wrote them as scalar equations. I didn't put vector signs over them. But those are all vector equations. You put vector signs on everything that's a vector. Time is not a vector. There's no direction to time. But if you put vector signs over everything, those are all correct above the black line. Below the black line, this is not a vector equation. You can't have a vector speed squared. It's, in what direction would square speed be? We can't do that. So the one below is not a vector equation. However, when we learn to solve problems in 2 dimensions, so we'll have, for instance, vertical motion and horizontal motion, we can still use this equation for the horizontal motion. And we can use it for the vertical motion, but it's not a vector equation. All right. Any questions as I move along? I don't want to just leave people behind, say things, and assume everybody knows. Michael.
We're going to have to know these for test, or we have to...
Okay, it's a very good question. Are we going to have to know these for the test? On the test, I will give you all of the equations you need. You don't have to memorize an equation. But you do need to know what the variables are and how to use the equations. So I'm not asking, my honest opinion is we can all memorize stuff. And it's really not a sign of anything, but you spend some time memorizing. In physics, we're looking for you to show your thinking that you've processed and analyzed. And so we give you the things that would require rote memory. Right? If you've taken any classes on the hierarchy of questions, right? We cut out the lowest section, the rote memory. We just don't care about that. What we want is the higher levels of the questions, which, of course, as a student is not always welcome. You know, the questions you have to really think through are, well, they're harder than the ones that you're like, oh, yeah, 5. But in physics, that's what we're focusing on, the ones you have to think through.
So is a summary of the variables x is distance?
X is position, yeah. And actually, different textbooks use different variables, and it depends on the situation what variable will be used. Very traditionally, we use x for one-dimensional position. If we have two-dimensional motion, we use x for like horizontal and y for vertical. If we have three-dimensional motion, we use x for horizontal in one direction, y for horizontal in the second direction, and z for vertical. Right? Those are conventions. You don't have to follow them. Textbooks usually do. We also have some other variations. We have r that is used for radius, and sometimes it's used for the position vector. We also have s that is used for the path, often used for if you have like a curving path, how far you are along that path. So there are some additional variable names that will come. But right now, yeah, x is position. And when we work vertical, I'll probably start using y for vertical.
So can you explain that horizontal line thing again? A vector. So you said
The near horizontal line. Yes.
The black one.
The equations above that are quite technically vector equations. That is, if I put a vector sign here, well, let me get rid of the tool for lines so I can actually draw a vector sign. A vector sign here, and a vector sign here, and a vector sign here. That's correct. And that's correct. And that's correct. And that's correct. Right, they're vector equations. The position vector is equal to the initial position vector plus the velocity average vector multiplied by time. So I can have two-dimensional, three-dimensional motion. The equation is still correct. But this bottom one, you can't do that because there's no such thing as v vector squared. Okay, let's look at our pretty diagram here. Here we have a picture of a person dropping a ball. This should be highly familiar to you, right? This is what we did in lab this week. We dropped the ball. It was probably not super scintillating. You know, watch the ball drop, start the timer, stop the timer. The goals for the lab were for us to understand errors inherent to a process like this. The goal of the lab was not actually to understand gravity. We hadn't talked about gravity in class yet. But you were to think about what might cause it. A number of people did say gravity. Some people had even better, gravity and air resistance working together. In this class, as in all general physics classes, we pretend there is no air. There truly is air. if you were to, I don't know, be snow skiing. Back in my younger days, I was sponsor of the agency association at PUC, and we'd go on ski trips, and I'd be skiing with the kids, and we'd be racing. I'd get down in my tuck, I'd blow them away, because I had 203, some long boards, and then one day, I was going really fast, went over just a little roller, and just flew, and crashed quite harshly. I actually had time to, in my boots, walk up about 30 yards, get my ski, and hand it back on before the guy was racing past me, but I lost. But it hurt. And so after that, like the next year, Jason Wong and I went out to race again, and I started going, got fast, and I got scared, and I stood up. Okay, all of this to explain the physics makes approximations. What happens when you're skiing fast and you stand up? Did not go faster. You slow way the heck down because you have huge air resistance. Right? That air is a very noticeable effect. And I was really embarrassed because I'd be going fast, beating him, and then I'd be scared, stand up, he'd catch up, so I'd get back down to my crouch. Really embarrassing, so I stopped racing after that. What's the point when you're scared to race? But we have big air resistance. Even as a little kid, driving from Santa Cruz to Monterey Bay Academy, I'd have my hand out the window, feeling the air blowing my hand back. That's wind resistance. It's very real. But for general physics, we will pretend it doesn't exist. We will pretend that if you put your hand out the window and you're driving down the road at 80 miles an hour, nothing. Okay? Unless it specifies that we're to include it, we'll pretend it doesn't exist. Now, is that a good approximation? Depends on what you're doing. For our lab where we were dropping this little ball, just 1 meter or 2 meters, it was a pretty solid approximation. But if we had been, jumping off of the Dick building onto some kind of, safe thing, it would not have been a good approximation at all. The air resistance would have slowed you down quite a bit. I mean, there are cases where people have fallen out of airplanes, flying up there at over a mile altitude and not been killed when they hit the ground. Clearly, it's because the air slowed them down. Parachutists, they jump out of the airplane, they reach a terminal velocity where the wind resistance, which is a force, pushes up with an equal force to the force of gravity pushing down, and they reach constant speed. Okay, so we will approximate what about air resistance? That it doesn't exist unless we're specifically told to include it. So in our problems, such as in lab, we assumed air resistance didn't exist. That would be a source of error, right? The goals were to look at sources of error. So that would be a source of error. How big was the source of error for us dropping a little ball 1 meter? Very, very small. What were the big errors we had in dropping that? Reaction times. And there were a number of students who said, we could have done this better if we used, somebody said if we had some little photo gates and used the photo gates to start and stop the timers. Those would be highly accurate. And so we would have had highly accurate times. Now, if we'd also had something to measure the distances highly accurately, we could have had really, really good data. I didn't go with the most accurate we had available to us because I wanted people to evaluate the sources of error that are present. And your reaction time is different for the drop than it is for when it hits the ground. Because with the drop, and there was at least one student who pointed this out, let's say Chad's my partner and Chad drops the ball. I'm sitting there looking at that ball, concentrating, and as soon as that ball drops, I hit my starter, and I'm going to have a delay that's more than 1/10 of a second. No, humans just can't beat that. There are a few probably. But for most humans, that's the best you're going to get. It's like 1/10 of a second. But when it hits the ground, I'm not an idiot. I see it coming toward the ground. I know it's coming, it's going to hit it now. And I can time it. And so my reaction time is not nearly as big of an error for hitting the ground as it is for when it drops. Now, of course, my reaction time when it drops is going to make me slow to start. And so that makes everybody's time shorter than the real time because they were slow to start, but they stopped it on time pretty much. So it makes sense why most people had times of like 0.3 seconds, because they had a delay of at least 0.1 second for starting and then very little delay for stopping. Now, how long should it have taken to drop 1 meter? Well, we just use these equations. At least of what I've graded, there was one group that went through and calculated what they should have been. You take these equations. We want to solve the problem. How long is it going to take for... Okay, just have to make sure class isn't over yet. How long is it going to take for it to fall 1 meter? Well, we have these equations. We have the starting and ending positions. So if I have the starting and ending positions, what can I decide about the equation right off the bat? Okay, I have x's, so clearly the one with no x is not the correct equation. Not the correct equation in this case. I want to find the time. So I need the x's and I need the time. That's going to rule out the bottom equation. Hence, I'm going to use the top equation to find the time that it takes to drop 1 meter. Now, when you're doing a problem like this, you should always, and on the tests, you will be graded on this, you should always start by drawing an appropriate... Okay. Let's get out of the zoom mode. Start by drawing an appropriate figure. So for dropping it 1 meter, I'm just going to have, and I know there are a couple people who had a nice little picture with the meter stick and the balls here, and then it comes down to here. And up here I had my starting position, and I'll go ahead and use x0. I'll say that's 1.0 meter. 1.0 is about as good as we were getting with that experiment. You know, it could have been 1.1. That's saying you're off by as much as 10 centimeters. Well, no, we're better than that. But you probably were on the order of 1.00 with an error in the ballpark of a centimeter on your heights. And it's going to end up down here at x equals 0. I have the starting and ending positions. I actually write them on my figure. What about the starting velocity? It was 0 because you start it from rest. When you have 0, you don't have to use units. That's why there's no units here or here. I could put 0 meters, but oddly enough, 0 meters, 0 centimeters, 0 millimeters, they're all the same value. So you don't have to put units there. What about the acceleration? Okay, we have a very complete answer. Negative 9.80 meters per second squared. Now that's what we call the acceleration of gravity. We often will write this as minus g. That is, we define a constant. G is equal to 9.80 meters per second squared. The constant is positive. It's not a vector. It's a scalar. It doesn't have direction. The acceleration of gravity is what defines down. So if I take a ball, I can always determine the direction of the acceleration of gravity. Remember, no air resistance in my physics world. I drop the ball, the direction it falls is by definition down. And so the acceleration of gravity, the vector always points down. In my problems, I consider up positive. So I should draw on here an arrow with the x pointing up to indicate that I'm considering x positive in the upward direction. And since my acceleration is downward, it has an arrow like that, opposite direction for the arrow, so the minus sign. So I could put minus g or minus 9.80 meters per second squared. Now, reading through the textbook for today's class, you probably noted that g is not the same everywhere on Earth. G ranges between about 9.78 meters per second squared up to 9.83 meters per second squared, depending on where you are on Earth. The things that affect that are, number one, how close you are to the center of the Earth. Most of us have been to, Colorado. You go to Pikes Peak. Pikes Peak, you're 14,000 feet above sea level. You're a fair distance farther away from the center of the Earth than you are here in Lincoln, Nebraska. And because you're farther away from the center of the Earth, the acceleration of gravity is slightly smaller. Or to put that in layman's terms, you lose weight when you go to Pikes Peak. Now, you don't lose mass. You're not any skinnier, but you lost weight by going there because the acceleration of gravity dropped. On the other hand, if you go to a low elevation, of course, I mean, you go to the lowest elevation on Earth, and it's only like, 100 feet below sea level, so it's not a big difference. But the closer you are to the center, the higher the acceleration of gravity would be. Also, the Earth is not shaped like a sphere. The Earth spins, and because of that, it's fatter at the waist, just like some of us. And because it's fatter at the waist, if you're at the equator, you're farther away from the center of the Earth, and the acceleration of gravity is smaller. If you're at the poles, you're actually closer to the center of the Earth, and the acceleration of gravity is bigger. And so that's where you have your extreme values for the acceleration of gravity, poles versus equator. Okay, continue on with this. I have my x initial, my x, my v, my a. I have one more variable that I don't know. I know I'm going to start with t initial is 0. I'm not even going to write it down because we took that as a given. And so I am looking for the time. So I will put here time equals to remind me, hey, that's what I'm looking for. So I've written down all of my variables on a diagram that illustrates what's happening. And now I've determined already which equation. When we're solving physics problems, the first thing we do is lay it out like this. Then we say, okay, what ideas are involved? At this point in time, we have one idea, the kinematic equations. Hence that what ideas are involved is a very quick step right now. But later on, we'll have more things involved, and it'll be more thinking to determine what's at play. So we determine it's the kinematic equations. Then we determine what equation. I actually started with that analysis, but in the normal sequence, after I determine it's kinematic equations, then I determine which one. Then I do my work. So I've determined the equation I'm going to use is and then I just put in my values. Now, there's the master problem solver way and the beginner problem solver way. The master problem solver way is what you will be moving toward. The beginner is assumedly where you are now. The beginner problem solver way says x means nothing to me, but 1 meter, that means something. The master problem solver says x means position, that's very meaningful to me. 1 is just a number, right? It's a different way of looking at the information. So the way I solve the problems, the way all physics teachers solve the problems, is the master problem solver way of noting the variables and keeping the variables until the end. That way you can see, okay, this is what would happen if the value increased or decreased. But I do put in zeros right off the bat. So my x final is 0, my v initial is 0, so I put those in to make my life easier. Then I'm left with 0 is equal to x0 plus 1/2 at squared. Well, my a is minus g, so I'm going to substitute for a minus g. And then I need to solve it for time. So to solve it for time, I will move this across. Minus x0 is equal to 1/2 minus g t squared. Multiply both sides by minus 2 over g. And I get, notice this 2 cancels with that. That's why I got the 2. This minus cancels with that. That's why I have the minus. This g cancels with that. And so the right side is just t squared. The left side is minus times minus is plus 2x0 over g. Finally, square root both sides. T equals plus or minus square root 2x0 over g. I have a plus or minus there. That's a mathematical step. Anytime you do square root, you have 2 answers. Right? Minus 3 squared is 9, just like plus 3 squared is 9. So you have 2 answers anytime you use the square root. But my brain tells me that the ball isn't going to hit the ground before I let go. And so I can use my brain to logically rule out one of those. And so I know the correct answer is only going to be the positive one because the negative one's not possible. And so the correct answer is the time is equal to the square root of 2 times my initial height, 1 meter at 1.00 meters, divided by g, 9.80 meters per second squared. Remember, g is a positive value. If you have a square root of a negative number, you get an imaginary answer. We don't like imaginary answers because they are surprisingly not real answers. And you do that, and it's, what, 0.45 something seconds. So that's how you can actually calculate the fall time. And you could have calculated, for instance, the speed at any moment during the fall. And that's what you have in this picture. You have the position at any time, well, at these specific times, 0.1, 0.2, 0.3, 0.4, 0.5 seconds, the speeds at those times, and the time. Just use these kinematic equations to find them. Graphs. We are going to focus on graphs in lab tomorrow. So given that I only have 2 minutes left, I'm going to forego any discussion on graphs because I wouldn't get anywhere, and at least look at how I would set up the first of my two problems. A dragster starts from rest and accelerates at a constant rate of 1 g. What does that mean to have a constant rate of 1 g? Right, it's 9.80 meters per second squared. How fast is it going after 400 meters? I would start with drawing my picture. So it starts here with v initial is 0, x initial is 0, acceleration equals g, ends up over here with x equals 400 meters. And I'm looking for first, how fast is it going? What variable is conspicuously missing? It doesn't have time, is that what you said? It doesn't have time. So I'm going to choose the equation without time to find the speed it has at the end. So I will be looking for the final speed here. And I would have that equation. So my v, and I put this wrong. That's a mistake. It's not supposed to be final minus 0. It's final minus initial. And we're using final as blank. So the initial speed there was 0. The x initial was 0. And I want to find the v, so just solving by multiplying both sides by 2a. v squared equals 2x. And that's how I would find the final speed. Right? The process, right now, I can just go right to the kinematic equations because I only have kinematic problems. Drew the picture, knew what my variables were, found the equation that matched the variables. Okay, time to go. Remember, we have the pre-lab quiz before lab. Yes?
What can we do to prepare for that?
To prepare for that, well, the quiz is based on the lab guide. So just have your lab guide with you when you take it. That's it. Now, I thought you were going to ask, what can we do to prepare for lab? For preparing for lab, read through it. That's why you have the pre-lab quiz, to make sure you do. And then you can write down all of the beginning parts. You can work on your hypothesis so you have a good idea what you're going to do for that. You know, you can have something written down, just bring it in. Is this appropriate? And through the procedure. Obviously, you can't have anything beyond procedure. Maybe.
Last week, I looked at a message.
Let me stop the recording before I go on record.